Welcome back to AI.Code.Cast, your daily dose of algorithms. Today, we're going to be diving into a problem called minimum limit of balls in a bag.
Ooh, that's a good one.
It sounds pretty straightforward, but
Sounds like
tricky parts.
Yeah, it definitely has some hidden depth to it.
I
Let's
say hidden depth.
let's break it down. So, imagine you have a bunch of bags, right?
Mhm.
And they're all filled with different numbers of balls.
Okay, I'm picturing it.
Yeah, and your goal is to redistribute all these balls so that no single bag has too many.
So we're trying to kind of balance things out.
Exactly, yeah. You're trying to make sure the distribution of balls across the bags is as even as possible.
Okay, and what's the catch? There's got to be a catch, right?
Oh, there's definitely a catch. You have a limited number of moves.
Limited moves, huh?
Yeah, you can only split the bags a certain number of times.
So it's like we're playing a game, but with limited actions.
Exactly, yeah. And with each split, you can only divide a bag into two new bags. So we can't just dump everything out and start over.
No. It's got to be strategic.
Okay, I'm already seeing how this could get complicated.
And the challenge is to figure out, what's the absolute smallest possible value for the maximum number of balls in any bag?
So we're trying to minimize the worst case scenario.
Exactly, yeah. It's all about optimizing that final distribution.
Okay, so where do we even begin with something like this? What's the most obvious approach, even if it's not the most efficient?
Well, the first thing that might come to mind is brute force.
Brute force, huh? Just try everything.
Yeah, basically, you would literally go through every single possible combination of splits and see which one gives you the smallest maximum number of balls in a bag.
I can see how that would work, but it sounds incredibly time-consuming.
Yeah, especially if you have a lot of bags and a lot of splitting operations allowed.
Right, the number of combinations would explode.
Exactly. Brute force is rarely the most elegant solution. It works for very small inputs, but as the problem scales, it quickly becomes impractical. So we need something more clever, something that can help us strategically explore the possibilities without having to check every single one.
Exactly, and this is where a technique like binary search comes into play.
Binary search. Now, that's usually used to find a specific value in a sorted list. How does that apply to this problem where we're trying to optimize a result?
That's a great question. In this case, we're not using binary search to find a specific value. We're using it to find the optimal value.
The optimal value meaning?
The smallest possible maximum number of balls in a bag after all the splitting is done.
Okay, so instead of searching for a needle in a haystack, we're searching for the sweet spot in a range of possibilities.
Yeah, you got it. Think of it like this. You have a range of possible maximums.
Like if the biggest bag we start with has, say, 100 balls.
Right, then our range would be from 1 to 100, because you can't have a bag with 0 balls, and the biggest bag gives us our upper limit.
Gotcha. So with binary search, we're not checking every number from 1 to 100. We're jumping right to the middle.
Exactly. You start with the midpoint, 50 in this case, and you ask, can we achieve a maximum of 50 balls per bag using the allowed operations?
Now that's where things get a little tricky, right?
Yeah.
How do we actually determine if that's even possible? It's not as simple as just dividing the total number of balls by the number of bags.
Absolutely. And that's where we might need a helper function, that is.
A helper function. Intriguing. What does it do?
It basically simulates the splitting process and checks if we can stay within those allowed operations.
Oh, I see. So it's like a behind-the-scenes test run to see if our current maximum is even feasible.
Exactly.
Okay, I think I'm starting to get the bigger picture here. We're using binary search to efficiently explore different maximums, and this helper function is our way of checking if those maximums are actually possible.
You got it. It's a powerful combination. But before we dive deeper into that helper function, let's talk about some common pitfalls, things that trip people up when they first encounter this problem.
Yeah, what kind of things should we watch out for?
Well, a common mistake is assuming that we can just aim for an even distribution of balls across all the bags, like if you had 10 bags and 100 balls.
Right, just put 10 in each bag, easy peasy.
But remember, we have that constraint of splitting bags into only 2 new bags at a time.
So simple averaging might not always work.
Exactly, yeah. You might end up in a situation where, to get that perfect distribution, you'd need more splitting operations than you're allowed.
Okay, so even distribution is a tempting guide, but not always the right path.
Precisely. And another common question is, what happens if we have very few operations allowed?
What if we're really restricted in our moves?
Yeah. Does that make binary search less effective?
I would imagine it would make things harder.
Actually, it doesn't.
Really?
It still works just as well. Remember, binary search is about efficiently exploring that range of possible maximums, regardless of how many operations you have.
Okay, so even if our options are limited, binary search is still our trusty tool.
Exactly. It helps us zero in on the best possible outcome, no matter what.
I'm really starting to appreciate the elegance of this approach.
Yeah.
We're not just blindly trying things, but we're strategically narrowing down the possibilities.
And that strategic thinking is key to solving these kinds of algorithmic challenges.
Absolutely. Now, you mentioned earlier that using a separate helper function isn't strictly necessary. Is there another way to achieve the same result?
There is. We can actually integrate that split counting logic directly into our binary search loop.
Oh, interesting. So instead of going back and forth between the binary search and the helper?
We handle everything right within the binary search. It streamlines the code a bit.
Mhm. I'm intrigued. Can you walk me through how that would work?
Of course. But let's save that for after a quick break. Stay tuned.
Okay, so we left off with this idea of a helper function that simulates the splitting process. Can you walk me through how it actually figures out if a given maximum, our penalty, is achievable?
Yeah. So imagine the helper function, right? It takes that penalty and it goes through each bag, like one by one.
Okay, so it's examining each bag individually.
Exactly.
Yeah.
And for each bag, it figures out, okay, how many splits would we need to get all the balls in this bag down to, at most, the penalty size?
So, like if we had a bag with, let's say, 15 balls, and our current penalty was 4.
Okay, yeah. So you've got 15 balls, and you want to get them all into bags that have no more than 4 balls each.
The helper function would calculate how many times we need to split that 15-ball bag to make that happen.
Right. You got to split it strategically.
Let's see. One split would give us 8 and 7. Then we'd have to split the 8 to get 4 and 4. And then the 7 would need 2 more splits to give us 4, 2, and 1. So 4 splits total for that one bag.
Exactly. You got it. And the helper function keeps track of the total splits, for all the bags.
Okay, so it's tallying up all the splits we need across all the bags.
Yep.
But how does it determine if our penalty, that maximum bag size, is actually possible given the rules of the problem?
Well, it compares that total number of splits to the maximum number of operations, the moves we're allowed.
Ah, right, that crucial constraint.
Yeah. If the total splits we need are more than the operations we're allowed.
Then we know we're in trouble. This penalty is too strict.
Too ambitious. Gotta loosen up that penalty, allow for a bigger max.
So the helper function would signal back to the binary search, saying, nope, try a bigger penalty.
Exactly. Gotta go higher.
And what if the total number of splits is within our allowed operations?
Well, that means this penalty could work. It's feasible.
But maybe there's an even better solution, a smaller penalty that also works.
Right. So you gotta tell the binary search, hey, maybe try a bit smaller, see if we can squeeze that penalty down.
I see. So the helper function is like our feasibility checker, helping the binary search navigate towards the optimal solution.
It's the guide, leading the way.
I love how this approach is so strategic. We're not just randomly trying things, we're systematically narrowing down the possibilities.
And that systematic approach is what makes it efficient, especially for larger problems.
You mentioned earlier that having a separate helper function isn't strictly necessary. Can we actually achieve the same outcome without it?
We can. We can integrate that split counting logic, right into the binary search loop itself.
So instead of going back and forth between the binary search and the helper?
We do it all in one place.
Okay, how would that work in practice?
Well, picture this. We've got our binary search loop, right? And inside that loop, we add another loop.
Nested loops.
Yeah. This inner loop is going to go through each bag, just like the helper function did, figuring out the splits for each one.
And we keep a running total of those splits as we go.
Exactly. And here's the trick. If that running total ever goes over our allowed operations,
We know this penalty is too small. Got to adjust our search range.
bump it up, increase that lower bound.
But if we get through all the bags and we're still within our allowed operations,
Then we try to go lower, shrink that upper bound, and repeat.
until our bounds meet in the middle, and we've got our optimal solution.
Bingo. We've merged the helper into the binary search. Streamlined.
This is so clever. It's like we took 2 separate tools and combined them into one super efficient multi-tool.
It's all about finding the right approach. Both ways work, but this integrated way can be a bit cleaner, more elegant.
I'm really starting to see the power of these algorithms. We've broken down this seemingly complex problem into manageable steps. And it's all thanks to these clever techniques.
That's the beauty of algorithmic thinking. It's all about finding patterns and using them to our advantage.
I'm excited to see what other challenges we can tackle.
There's a whole world of algorithms out there just waiting to be explored.
Okay, so we've got this integrated approach where we're handling the split counting right inside the binary search. It's pretty clever.
Yeah. It's all about efficiency, right? Less
Yeah.
back and forth, more streamlined.
Right. So can you remind me again how it all works? We've got our binary search loop going, testing different penalties.
Yeah, and inside that loop, we add another loop.
A loop within a loop.
Exactly.
Yeah.
This inner loop, it goes through each bag, just like that helper function did.
Right, checking each bag one by one.
Yeah, and for each bag, it figures out, okay, how many splits would we need to make sure this bag has no more than penalty number of balls?
Okay, and as we're going through the bags, we're keeping track of the total splits needed,
Yeah,
right?
you got it. It's like we're adding up the splits as we go.
And if at any point that running total, that split count, goes over the allowed number of operations,
Red flag. Right, that penalty's too small, gotta adjust the search range.
we got to go up, right? Raise that lower bound.
Exactly, gotta give ourselves more room to work with.
But what happens if we make it all the way through all the bags and our split count is still within the limit?
Well, that means this penalty might be the one, but maybe we can do even better, right?
So we try a smaller penalty.
Exactly. We adjust that upper bound, shrink our search space, and keep going.
And we repeat this whole process, checking the bags for each new penalty until
Our lower and upper bounds basically meet, they converge.
and that point where they meet, that's our optimal solution, the smallest possible penalty.
You got it. We've found the most efficient way to distribute those balls.
This is brilliant. We've essentially merged two separate parts into one streamlined process.
It's all about understanding the problem, and finding those clever ways to optimize our solution.
Yeah, I'm really starting to see the power of algorithmic thinking. We can take a problem that seems really complicated at first, break it down into smaller steps, and use these powerful techniques to find the best possible solution.
And that's what AI.Code.Cast is all about. We explore these algorithms, we break them down, and we show you how they can be applied to real-world scenarios.
Exactly. It's not just about finding the right answer. It's about understanding the process, the logic, and the strategies behind these solutions.
It's about expanding your problem-solving toolkit and being able to tackle those tricky challenges with confidence.
I love it. Thanks for joining us on this deep dive. We hope you learned something new today, and we'll see you next time for another algorithmic adventure.
Keep those brains working, and remember, the most elegant solutions often come from thinking outside the box and applying those algorithmic principles.